Okay, let's start. So, last time we discussed semi-discretization of parabolic initial boundary value problems in the sense that we discretize in space in the way we know it already for the corresponding elliptic, for the corresponding stationary problems. And now, opposite to the linear sets of equations which we have got as a discrete problem to be solved in the stationary case, we now get a system of ordinary differential equations. And as we are further on dealing with linear problems and further on applying linear schemes to linear problems, these are linear systems of ordinary differential equations, which can, at least in principle, solved explicitly. We have taken advantage of this in a theoretical consideration. In principle, if the matrix is such that we know that there is and that we know an eigenvector function, eigenvector basis of this matrix, which in general, of course, to compute the eigenvalues of a matrix is a much more complicated task than solving a set of equations or solving a sequence of set of equations. So there's still something we should do, namely to do time discretization in addition, which we will start with today. But for this first intermediate step, we have seen now various convergence results. We tried a little bit heuristic approach for the finite difference case for our very specific model problem, comparing the two representation of solutions, and we have seen, okay, there are these higher frequent eigenfunctions in the continuous case, so to speak, up to infinity, which do not exist in discrete case, but they are damped very strongly, at least away from zero. That is the important thing there. So this is an error part which is more or less negligible, and in the remaining part, the things are comparable to the right order of convergence. So the deviation in the eigenvalue is of the right order of convergence of h squared, and the deviation also in the Fourier coefficient is like that, and the eigenfunctions in this particular case even turn out to be exact at the grid. Okay, now in the finite element case, the analysis is a little bit more satisfactory, and what we have shown there is that we can show pointwise in time, that is meant by this here, this situation, pointwise in time, but only in the L2 norm, not in the norm we are used to have as the natural norm, namely the energy norm, the H1 omega norm. We can prove something which is very similar to the behavior we have seen from the explicit representation of solution. We have a part which reflects the initial error, the deviation between the initial data and the Ritz projection of the continuous initial data, damped with an exponential term with the ellipticity constant here. We have the Ritz error, the error of the Ritz projection, so to speak, that reflects what the corresponding stationary problem has for accuracy for each instance in time. So you see, we need already more regularity for the solution ut that this thing makes sense, that we can write this thing and do these manipulations rigorously. So we need not only have to have an L2 function in time with values in h, in L2 of omega, but we need something like a continuous function, which we also would have. But here, for further estimate of this term, we need then more, and in particular, we have this term here, which is basically the same thing as here, but now for the time derivative. So also the time derivative has to be something like a continuous function in time with values in h. And this influence is now again, it goes back over all the past, 0t, but is again damped in time as we have seen it for the right-hand sides of parabolic equations. And the background of this proof, and maybe I come back to that because this was maybe a little bit confusing what I said. So what we do is we have to estimate the error here. We subdivide the error into two parts, namely the deviation between our, say, finite element solution in the semi-discrete case and the Ritz projection. So this is something which takes values in VH. This is called theta. And then we have an additional term, which is just the error of the Ritz projection, which appears here. So if we are able to deal with the first term, and if to deal with the first term leads to the first and the third term in the estimate, the overall result is just got by this identity via the triangle inequality in L2. So how do we get an estimate for the first term, for the theta, in terms of these in the first and the third term here? As we are in a discrete case, we can, what we can do, that we can do always, we can test with discrete test functions, with VH functions, but we are in the discrete case, we have now, so to speak, the defining identity for the Ritz projection saying what was the defining identity? Maybe we go back. Under the A bilinear form, VH for discrete test function is the same thing as the A applied to the Ritz projection at VH. So in this sense, we can take advantage of this, and maybe not to go through all the details of the proof again, this ends up that we get this type of equation for this first part of the error here. This is just algebraic manipulation plus this definition. So that means we have for the theta part, we have again such a weak form for a parabolic problem with a corresponding right-hand side. There we have seen already the stability estimate for saying there is, what is the estimate? It's the initial value correspondingly damped, and it's the right-hand side also back in the past also correspondingly damped. And here, and that is there I pointed to the, so to speak, the wrong line in the proof. Here at this place, we need the exchangeability of the time derivative and the Ritz projection applied to a time-dependent function. Because what do we have here? By definition, we have here, we go back, so we have the time derivative of rho, and rho is, where is it? Rho is this part here. So we get the time, in the second part, we get directly the time derivative of u prime, that's what we have. But here we get the time derivative of RH of ut. And this we would like to interchange with RH of the time derivative of u. And at that place, we did that. Okay, so what can we do now with this estimate? We can now immediately transfer this in an order of convergence estimate. Namely, we can say that if the Ritz projection is such that the Ritz projection produces an order h square. This is now a little bit it's not really perfectly noted. So here, okay. So what do we have to have? We have the corresponding order of convergence for the Ritz projection. The Ritz projection is nothing but the, so to speak, old finite element procedure for the time-dependent case. So there we know that we, under certain circumstances, we get h square for L2. What kind of circumstances are those? So we would have to have h in the energy norm that would apply typically under the corresponding regularity assumptions for the linear ansatzes or the bilinear or trilinear ansatzes on triangles or cubes. And then we must be in a situation that we can apply the Aubin-Nietzsche argument. That means we need this regularity, but not of the corresponding boundary value problem, but of the adjoint boundary value problem. Regularity in the sense that we have, if the right-hand side is in L2, then the solution is in H2. So we get this full smoothing over two levels by the equations. There's nothing in the equation which prevents us from having this. There's no problem with the boundary of the domain. There's no problem with the coefficients. Okay, so if we have an estimate like this, but not only, and this is a little bit non-perfectly noted here, that it's not only required for ut, it's also required for u prime of at t. So that means the function u and also its time derivative has to take values in the h2 of omega. So then if the approximation of the initial data is correspondingly of this order of h square, then we get an order of a convergence h square, because then we can go back to this estimate and say, okay, we have here a term which behaves like h square. This is even then damped in time very strongly. Here we have a term which behaves h square. There's no damping. And here's also then a term that behaves in h square correspondingly damped here. At least for the past. Okay, one can write this a little bit more abstract and say, okay, what do we need? We need to have that in the corresponding underlying basic space, we have at least an order of h. And then we have to be in the situation that we can allow for, as I said, for the Aubin-Nietzsche argument. That means we need our standard assumptions. The bilinear form must be V elliptic, continuous, but in addition the solution of the corresponding adjoint boundary value problem, or the adjoint to A, so with arguments exchanged. We discussed what that means in principle. Basically means that we take the convective term and look in the other direction of the wind and change correspondingly the boundary conditions. But it's very similar to the original problem, of course, in the symmetric case. It is the original problem. Then, under these assumptions that we have both the regularity and we have both this order of convergence estimate for the underlying space Vh for correspondingly for H2 function, for functions in V and in H2, then we can show the following estimate. That's basically the same what we had already. If the initial data is in H2, in addition, if the solution is sufficiently smooth in the way I just discussed it, then we can estimate the error pointwise in time. So what we have here, the norm in space and time we are dealing with here is the L infinity, 0t, with values in L2 of omega, with values in capital H. Because we have here a pointwise statement. It's not an integral in time which appears here. It's pointwise in time, which also reflects the smoothing which we have by the parabolic equation. So what do we have? We have the initial error. It is as good as it is and correspondingly damped. Of course, to preserve an overall h square situation, then one would say, okay, also the initial data should be represented of the order h square, and then we have this h square term, which comes from the approximation of u0 by the Ritz projection. This is this part. By its Ritz projection, this is this part, also with the damping. Then we have here the ut in the H2 of omega norm without damping, and here we have correspondingly this term here for the time derivative. So we see overall we preserve here, without doing any time discretization, we preserve the spatial order of convergence, and we have an exponential decay of some of the influences, basically of the influence of the initial data here. Okay, so yeah, the proof basically it applies. The proof follows directly the lines I just indicated. So we have to combine this estimate with the Aubin-Nietzsche result, and here in this first case, we just have to apply the triangle inequality we put in between the Ritz projection. The error in the Ritz projection is then estimated by this term, and the remaining thing is then this term here. Because the other way around. We have to deal with this term with the Ritz projection. We put in the boundary, the discrete initial values we want to use. That might be the Ritz projection, but also something different. For example, just evaluating the function. If it's smooth enough, that would be the most obvious choice to take as initial conditions, as we do it in the finite difference method. Then we would get here some error. So we would then have here, putting the exact solution in between, we would have this error here. So for example, an interpolation error, and in addition, the Ritz projection error. Okay, now let's go to the full discrete case. So which kind of methods you know to discretize initial, or do you know any methods to discretize initial value problems for ordinary differential equations? Are there any example which you know, which you would recommend me now to use here? Tell me a few words, a few names. Is there anything you remember? If you have the problem to discretize an ordinary differential equations, which pops up somewhere, 5 components, nonlinear, whatsoever, which kind of method you would like to use? You can do it in MATLAB, you could do it in COMSOL, but you have to push the right button. You have to select a button. Scientific work is reduced to pushing a button, but still you have to select one. Which one do you select? What names do you know? You should know a few names, huh? Shouldn't you? Runge-Kutta is one name. Yeah, there's... Okay, why Runge-Kutta? Runge-Kutta is a whole family. Do you have a specific suggestion in this family? Do you want to suggest me there are explicit and implicit Runge-Kutta schemes, and there are Runge-Kutta schemes of basically any order? What would you like to suggest to me? Let's say we do finite, we do quadratic elements. We do quadratic elements on triangle. That is, we have an order of h to h3 if the smoothness is correspondingly. What kind of Runge-Kutta we would like to suggest to me? First, explicit or implicit? Explicit is somewhat simpler. So we should take this, or shouldn't we? Okay, in which order? A very classical Runge-Kutta method is the explicit Runge-Kutta method of fourth order. I would hope you have at least heard of this one. You have seen this one. If you don't know anything, and if you go, your knowledge is dated back 100 years to the dates of Runge and Kutta, you would possibly take this method. What would you expect to get out? Fourth order means we get a fourth order term in time. a delta t to the fourth. Seems good. That is even better as the H3 that we have. And we could also maybe take one of third order. Then we would say, okay, we have the same order in space and time, and so we need to have the same fineness of discretization in space and time. Will this work or will this not work? What are the general assumptions that a Runge-Kutta method works? What you have to estimate? What you have to know about the right-hand side f if you deal with a system of ordinary differential equations y prime equals f of t and y. What kind of properties this f has to have? Maybe nonlinear. We are here the linear case, much simpler. But what kind of estimate enters in all these order of convergence results? What do you have to control to be sure that there's even a solution, that there's even a unique solution of your problem? We mentioned this last time. What does Picard-Lindelöf say? What do you have to control? Exactly. You have to have something like a global Lipschitz continuity in y of the right-hand side. What does that mean in our case? In our case, it's very simple. It's linear. It's a times y. So what we have to control is the norm is the condition number of the matrix A. But what does happen with our condition number? How does the condition number of our stiffness matrices behave? Are they uniformly bounded in H? No, they explode in H. So that means if we have a very, very coarse discretization with 5 spatial points, Runge-Kutta to the order 4 is wonderful. But if we have 10,000 points or 10 million, then we would get in trouble. Because that would mean we still would have a Lipschitz continuous problem. We have finite dimensional problems in space. Is Lipschitz continuous, is bounded. But we would have a tremendous Lipschitz constant. And to cope with this tremendous Lipschitz constant, we would have to take astronomically small time steps. Time steps which are much smaller than it would be required as in terms of accuracy. So we get in the conflict of accuracy and stability. We have highly accurate methods, but they don't have the right stability. So this is a problem in designing time discretizations for parabolic this is independent of the type of spatial discretization you use. All these discretization matrices behave asymptotically the same. There's no difference whether you apply finite difference or finite elements or later on maybe finite volumes or whatever new techniques appear. That's always the same. So the problem is this matrix we have to deal with. This has an exploding Lipschitz constant. So what we are going to do now, we are very moderate. We're going back to one very simple class of methods, which has a very restricted possible order of convergence, and we investigate the stability there. And later on, after having done this, we will try to put the things together and then get order of convergence estimate for the fully discrete method. Having both an error term, of course, in a corresponding order, and a temporal error term in a corresponding order. So let me introduce this method. You will recognize that that there are Runge-Kutta methods. They are very simple Runge-Kutta methods, either of the explicit or of the implicit type. But that is not so much the issue here. We call this method the one-step theta method. So the theta will be a parameter between 0 and 1, including 0 and 1, defining the method. And let me tell you how this works. So we do it similarly as one derives difference methods for ordinary differential equations. First of all, we have our time interval. Let's assume the time interval is finite. And then we subdivide the time interval by taking certain time levels, time steps. In a practical code, these time levels would not be equidistant, because one would use the information which we had gathered about the behavior of the solution and have some estimate whether one now should do a small or a big time step. For the simplicity of notation, I now assume that all the time steps are equidistant. But that's only to simplify the notation. So I subdivide the interval into n subintervals, and so I have to have my time levels, my time discretization points Tn, n equals small k, ranging from 0 to n. And correspondingly, this what is here called k, maybe it's a little bit of a bad notation. This corresponds now to the age. What was the age, or what is the age in the space discretization, is now here the k. It's just the discretization fineness. Okay, it's the time step size or Zeitschrittweite. And now we're doing it very, very simple. First of all, what we do is, we have only these time levels, and we approximate only solution at these time levels. At the zeroth time level, of course, we know the solution by the initial data. And the method now should enable us, having the solution at a certain time level, to compute the approximate solution at the next time level. That is a one-step method. It only refers to one time level back. There are multi-step methods, and I would hope you have only seen multi-step methods dealing with difference methods for initial value problems. That is the big other class, the multi-step methods, apart to the Runge-Kutta methods, the linear multi-step methods. Then one would go several time levels back. That would mean that one would have maybe two time levels, so we need a second method to give us an approximation at the first time level, and with the zeros and the first, and then we can get something on the third, then we take the first and the second, then we get something on the second, and then we take the first and the second, get something on the third, and so on. And of course, you could expand this then and have not a one-step method, but an, say, L-step method. And one can imagine that also the order of convergence depends on this. So we are now very modest. We are looking only at one-step methods. And to fix some notation, so one notation we use, one in the considerations is, of course, now the difference quotient to approximate some time derivative. So we just take values, whatever those values are, at the n plus 1 time level minus at the nth level divided by the time step size k. And if we need values in between, values which are in between the time levels, where we don't have information, then we just do it by the corresponding convex combination. So we would like to evaluate a function which we only have at, let's call it f, which we only have at the time levels, tn and tn plus 1, but we would like to have an approximation at tn plus s times k. Then we take the corresponding convex combination of the values here. And this number theta, that plays the role for this convex combination. Okay. This is now already the situation for the finite element case, but maybe I should start with the situation for the finite difference case. Now we are going, it's only a slight change in notation, it's exactly the same idea. So what do? We substitute, we only want to deal with information at the time levels. That is, in a way I explained it. So we have to write down everything in time levels. That corresponds to the finite difference approach, where we had to write down everything in quantities which were defined at grid points. So as I said already, for the time derivative, we use here the difference quotient, and you see here there's a change of notation, which is a little bit more natural of notation now. It's now here not called K, as in these old transparencies, and in the German version of the book, the time step size is here called tau. Tau is, I think tau sounds a little bit smaller than K. It's my impression that it's more natural to denote a small number by tau. Anyway, so the idea is now to say, okay, this is a difference quotient. This difference quotient substitutes the time derivative. The time derivative is supposed to be, according to our ordinary differential equation, minus a times ut. Now the question is, at which point t we think that this difference quotient is the appropriate approximation. We could say t is equals to tn. Then we would have then we would interpret this difference quotient as a forward difference quotient. We could also say t is tn plus 1. Then we would interpret it as a backward difference quotient. We remember, hopefully, that in terms of consistency, there is no difference between forward and backward difference quotients. It still would be in both cases would be a consistency of order capital O of tau. But we could also try to be a little bit smarter and say, okay, we interpret it as t as in the middle, so to speak, as tn plus 1/2 times tau. Then it would be a central difference quotient, and this gives us a higher consistency. Then that would give us a consistency order tau square. And to allow for all these cases, we do this with this parameter theta. So we now select the parameter theta and say we interpret this as tn plus theta of tau, or equivalently written as at the point n plus theta times tau. You see theta equals 1 was the forward difference case. Theta equals 0 was the forward difference case. Theta equals 1 is the backward difference case. And theta 1/2 is this hopefully better case in the middle, which will be later on Crank-Nicholson method. So what we are doing is, in the way I discussed, we now substitute but we do not have a times UH at this intermediate value, so we substitute with the corresponding convex combination, and as an abbreviation for 1 minus theta, I use here theta bar. That means the one-step theta method says compute a sequence of vectors un0, un1, and so on, with capital N, such that they fulfill. The first vector corresponds to the initial data, to the discrete initial data of the set of ordinary differential equations. And then all the other ones are supposed to fulfill those equations here. So the time derivative is substituted by this difference quotient, and the, let's say, spatial part at some time t is substituted by this convex combination. And correspondingly, as we now interpret this as an interpretation at this point in time, we also take the right-hand side at this point in time. So what does that mean? The simple situation, and then we are back again to this distinction between implicit and explicit methods. The simple situation occurs if we take theta equals to 0. In this case, this term vanishes here, and here we have just a factor 1. And that means we just have if we can now resolve this equation for UHN plus 1, and this gives an explicit formula. We multiply with t. What does that mean? We have to evaluate the corresponding right-hand side at n times tau. Then we have to have the old time level, which we know, do the multiplication with A. So we need again a matrix times vector. We are used to that. Multiply by tau. Combine this, and this gives us the new time level. And then we go on. This is an explicit method in this sense that it only requires matrix times vector operation opposite to the necessity to solve linear sets of equations. If we would, at the moment, there's no reason not to take this method, and no reason to take something different. But maybe we should still discuss this and do something different. So here it's again written down explicitly what I just said. You see here the formula resolved, and that is what we have to do. Do this multiplication, evaluate this term, do this Saxby operation, and then add this known vector. Or more in matrix notation, that is the matrix identity minus tau HH, with which we have to multiply the known vector at the right-hand side, and this gives us the new time level, and then we go on in the corresponding time loop. That method is called the explicit Euler scheme. Okay. I will chop up my right hand. If you have not seen this scheme dealing with corresponding Runge-Kutta schemes, because it's most simple explicit Runge-Kutta scheme, sometimes also called the polygonal method. You can also use this, and that is very natural, to prove an existence theorem that would be even without the corresponding Lipschitz, global Lipschitz assumption. That would be the existence theorem of Peano, which you can prove in this constructive way. Okay, so this is very, very simple, tempting to do, but you can imagine it will have drawbacks. Okay, so now if we would let's think of other methods, and specifically these two theta values 1 and 1/2. Maybe we go back to this formula, and you see what we have to do. Let's now look at the selection theta equals 1. That is called the implicit Euler method, and it's the most simple implicit Runge-Kutta scheme of first order. So what do we do? What do we have then? Then we do not have this part here, the old time level, but we have here also the new time level involved. So to get the vector at the new time level, we have to solve a set of equations, and the set of equations has the system matrix, if we multiply with the tau, identity plus tau AH. Or write it more formally, the way to get the new time level is to apply the inverse now of 1 plus tau AH. So the effort is now higher. We have to solve a set of equations. Now it depends a little bit on which kind of methods you are applying. If you apply, because here in our situation, with coefficients in the elliptic operator which are not time dependent, we always have the same matrix here. That is something one can take advantage of. You can also think of what would change if we would not have this situation. If we would have a problem where also the coefficients in the elliptic operator would depend on time, then everything would stay the same, but our matrix AH would also depend on time. That means we would have to evaluate here this matrix on the corresponding time levels, or if we have it given in an analytical form for all instances of time, we can also evaluate directly at this intermediate value. So that would mean we get exactly the same problem, but the matrix A is changing from step to step. But here, now let's see what are the consequences for the different ways to solve the set of equations. If we do iterative methods, there's no difference between these two things. Or say it another way, for iterative methods, we cannot take advantage of the fact that the matrix stays the same. The only good thing is, in terms of iterative methods, is that because we always have a good starting value, because we're doing time steps, and these time steps will be not too large. So we expect that the UN, the solution at the nth level, is already a good approximation for the solution at the next time level. And of course, this is something we can also control by selecting the time steps not equidistant. If we would select the time step not equidistant, of course, then also the matrix changes, because the matrix we have seen here in this case was identity plus tau times A. So if one of those two factors changes, then the matrix changes. But if the matrix does not change in this most simple case here, then one can take advantage of that applying direct methods, because that means when you only have to do an LU decomposition once, because the matrix is the same, the only thing what changes is the right-hand side in the set of equations to be solved, and we don't only have to do a forward-backward substitution. Okay. So now that was this kind of formulation, this explicit formulation, and what do we do if we have a more implicit formulation? For example, if this comes from a finite element discretization, where we've seen actually here the mass matrix appears, then the corresponding formula would be this one here. And now we can argue either as we did it in the theoretical fashion, that means we take advantage of a corresponding decomposition of the mass matrix and transform the mass matrix away, so to speak, or we just keep it as it is. And you see the modifications is only slight. The system matrix which we have to solve in the theta to 1 in the implicit Euler case is now not 1 plus tau times AH, it's just B plus tau times PH plus tau times AH. So in terms of effort, hardly anything changes. Okay, so and now there's also and what we have seen for the theta to 1 case, that in corresponding the effort, that also applies. Ups, was ist now passiert? Das geht nicht. Kann man das noch bewegen? That also applies to all the other theta values. So at the level of discussion we have now, there's no reason to apply theta to 1. Theta to 1 produces much more effort than theta to 0. Implicit Euler is produces much more effort than explicit Euler. On the one hand side, I have to solve a set of equations, have to set it up, and so on and so on. On the other hand, I only have matrix times vector operations. But this sort of conflicts with the fact that maybe in 95 of all computations done whatsoever, the implicit Euler method is used. And we have to find out what is the reason for that. What is the advantage of the implicit Euler method? It cannot be accuracy. Accuracy is the same. If we head for accuracy, then we should take the theta equals to 1/2 situation, what is called the Crank-Nicolson method. Okay, so maybe let's write down a few formulas that we see what we are doing here. And the formulas are here. Oh, Ups. Das muss doch beweglich sein, das blöde Ding, oder? Entweder ist es zu fest oder ich breche es gleich ab. Okay. So in each step we have to solve. In each step we have to solve a set of equations. Ja, das bringt es auch nicht. Aha, das ist die Lösung. Das ist die Lösung natürlich. Maybe we make it still a little bit. And we have seen how the system matrix looked like. The system matrix is formally written this matrix. 1 plus theta tau times AH. You see, you remember in the case theta equals to 0, there's nothing, it's just the identity. In the case theta to 1, that is the one we discussed, and in the general case is this matrix. And if we work out, if we only look now to the initial data, and we forget the influence of a right-hand side for the moment. So what we have to solve a set of equations for modified initial data. This is, so to speak, bring the known stuff to the right-hand side. So in the first step, we would have a right-hand side identity minus theta part tau or AH times U0. Then we have to solve the equations with this matrix. So we get this formula for n equals to 1 for the first level. In all the subsequent levels, it's exactly the same operation. That is, we get exactly the same matrix on top of this term. That is, on the nth level, we have here the nth matrix. And you maybe remember, if you have a, so the point is, if you have a fixed point equation, a linear fixed point equation, or sometimes also called a difference equation of the time, the new vector, and say xm plus 1, is a times ax. Then, of course, the solution is, at the nth level, the nth power of a times the initial vector. And that's exactly what we have here. Then we have the influence of the right-hand side, and that's a little bit more complicated. And then you see the same matrix appears here, but now, so to speak, with different powers. The more we go back in time, the higher the powers are, and here the whole past enters here. And you see there's a strong similarity to what we have seen what we have seen in the representation of the solution of the semi-discrete approximation. In the semi-discrete approximation, we had here e to minus ah times tau times n, or we can also write it in another way. We had here a matrix which was e to minus ah, and this matrix appeared in the nth power. And the same thing here. So what here apparently has happened by the time discretization is that this matrix e to the minus argument is now a matrix now, is substituted by this rational function here. And maybe you have heard the word Partieller approximation. Who has heard this word already? If you have not heard this word Partieller approximation, and you had a course which was called discretization methods and so on, you should go immediately to the Dean of Studies and ask for your money back. But maybe you have just forgotten about this word. So this is the central word, Partieller approximation of the exponential function. Okay, but don't worry. I told you, it's never too late in life. When I was at your age, say 42 years ago, and I had to do numerics, I totally ignored it. So being in the 6th semester or so, I had no idea what numerics is. And then I thought, okay, maybe you should do something with which you can earn some money later. And then I learned numerics on my own. Then I became tutor in numerics. And now, after 42 years, I know it a little bit. Anyway. So what we have here, if we now compare with... so what is the situation? Apparently, what we have is on the discrete level. On the semi-discrete level, we have this matrix, a to the minus AHTN. And this matrix appears times the initial data. And this gives then the solution at the nth level, only dealing with the initial data. Here, on the fully discrete level, we have another matrix. We have this matrix here. And you see this matrix comes to existence if we take a rational function that is the function 1 plus 1 plus theta part times x and over 1 plus theta times x, and we plug in this rational function in the way we discussed it last time. So how can one define, how can we plug in a matrix into a function, and we plug in the matrix tau times AH. And that's the same thing what we have here, because here we have just, so this is, what is the so if we, so to speak, take the nth power out, so we have this Eve matrix, and here we have the matrix e to the minus AH times tau, because Tn is n times tau, so this is nothing but the matrix I mentioned to the power n. So that is, so to speak, the correspondence between the terms, which we now see on the one hand side in the semi-discrete, on the other hand in the fully discrete, relating to the initial data. The situation with the right-hand side is exactly the same. In the semi-discrete, we have this term here. We have this E function, this matrix exponential, damping the initial data. Of course, this we can write in this way. We can say tau, this Tn minus s, is tau times Tn minus s divided by tau, and then in the exponential we take this power on top of the matrix. So what is the approximation we are doing? We said already the E matrix exponential is substituted by this rational matrix exponential. So small e goes to capital E, so to speak. And then we have an integral, and this integral is there. What we then done, we can interpret as a quadrature rule. So we have now the corresponding, ignore this term for a second, we have now the corresponding arguments in time, evaluated at the old time levels times t. So what we apply is just the rectangle, I'm not sure what it's called in English. In English, the Rechtecksregel. So we approximate the lowest order Newton-Cotes formula. In each small time interval, we approximate by a constant. So we get this constant value times tau. And the only variation which comes in is by this matrix. But you see, this matrix should not change too much because formally, if tau goes to 0, this matrix goes to identity. So in this sense, there are two things which happen. Substitute the matrix exponential by a rational exponential, and for the time-dependent part, for the right-hand side, apply a quadrature formula. That is what time discretization does. Okay. And that will be also the basis then to discuss the and such a rational approximation of the exponential function is called a Partieller approximation, and the table of Partieller approximation defines a whole class of implicit or the important implicit Runge-Kutta schemes. So what is written, now we formulate the whole thing again in the finite element context. It was a little bit general at the moment with a slight modification. In the finite element context, one would say we do not talk of vectors, we are talking of functions, and we would say, okay, we are looking for a sequence of functions in the discrete space VH, such that the U0 is identical to the corresponding approximation of the initial data, and then in general the UN plus 1 fulfills this equation. And you see this is exactly the same thing. Here we have the time derivative, the difference quotient, and here we have the corresponding convex combination of the levels in the bilinear form. Now it is a question a little bit what we do with the right-hand side. Here the right-hand side is denoted in a way that we do again the convex combinations of the right-hand side at the corresponding time levels. That is the idea behind that is that we only know it at the time levels if we know it for all instances of time. We have formulas for all instances of time. Of course, there's no reason not to evaluate directly at this intermediate value, if there is an intermediate value we are dealing with. So if we have a theta, it's a problem if theta is not 1 or not 0. Okay, so that is, so to speak, the variational formulation which comes out, and you see again, on the variational level, it's again now, we have now a sequence of variational problems, which is nothing but a sequence of sets of equations. It's exactly the same thing. The only difference is here that the theta is here written in another font. But I hope this is not too disturbing. Okay, This would now mean we go directly now in the order of convergence estimate, which I don't want to do. I really now want to discuss first the stability of the method, and so we have to go back here and look at the stability question. So, okay. What do? We have seen already in the situation where the matrix AH has an eigenvector basis, we have good tools to analyze the behavior, not so much numerical tools, because to compute this eigenvector basis is a big problem on its own, and maybe a stronger problem than what we want to solve originally. But in theoretical terms, we have something on our hand, and that we are doing now also. So from now on, we assume that we have an eigenvector basis again, and from some point on, we will also assume that this eigenvector basis is orthonormal. So you might say, in some sense, we are going back to the symmetric case. In the symmetric case, we are sure that these things exist. There are other cases where it exists. it might not exist. This is sort of an axiomatic approach. The eigenvectors are denoted by Wi and the corresponding eigenvalues by lambda I. So if we now, this is what we have seen already, and we have worked with this already. So this we have seen already. If we apply this matrix exponential to an eigenvector, it just means apply the matrix function to the eigenvalue, and then this is, so to speak, the new eigenvalue for this corresponding matrix. So this is again a matrix eigenvector, eigenvalue, eigenvector relation. This we have derived, and we've worked with that. Now we do the same thing with this special rational function which we have here. And what does that mean? That is even more simpler. If we now apply this matrix here to the eigenvector, what does that mean? It stays an eigenvector for this matrix because this is just a polynomial. And what does happen? So the identity there is 1, the shift of 1 minus theta bar tau times the eigenvalue. So we get this factor. For this matrix, forget the inverse, we would get 1 plus tau theta tau lambda I. And for the inverse matrix, we have just the inverse of the eigenvalue. So this is the way this matrix reacts to the eigenvector. Or to put it in another way, if we now restrict that is the nice thing with that, if we now restrict ourselves to eigenvectors, we can forget about all these matrix functions. These matrix functions go back to the normal real functions, and in the arguments the eigenvalue appear. So the eigenvalues are the characteristic values of the matrix. That is, we have to know what these functions do with the eigenvalues, and then we know what the full matrix function does. So we see now, and that is this rational function I've now mentioned quite a bit. Okay, so this capital R is just what we have on top, and the argument which is plugged into the capital R for the set is apparently done minus tau times lambda I. So this is important to notice, that minus the eigenvalue appears here. So this function R is apparently responsible how the solution develops. The reaction of this function R to the eigenvalues, and more precisely to minus the eigenvalues, and even more precisely to minus the eigenvalues times tau, reflects how the solution develops in time. And if we know how the solution develops, of course we also know how the difference of two solutions develops. We are dealing with linear problems. And if we know how the difference of two solutions develop, we also know how a perturbation of a solution develops. And we want to have maybe not necessarily a damping of a perturbation, as we have seen it already, but we want to have at least stability in the sense that perturbations do not increase in time. So that is something we have to look at. And as our eigenvalues are typically positive, we have to look for negative arguments in this function R. And more precisely, as we cannot rely on having eigenvalues which are real, we have to look at this function R in the complex domain, in the complex plane, and specifically on the left-hand side for negative reals. We have to see what this function does for negative reals. And if we cannot say anything about the full left part of the complex domain, the only thing we can play with is still the tau. We can make the tau small and then restrict ourselves maybe to a part of this left-hand part of the complex plane. But that would mean that we need time step restrictions. And this will come in some of the cases. Okay, so what we have seen is here, this is in the next formula. Let's first look at the situation only concerning the initial data. So we have seen, we repeat the whole discussion. This is the part which we have in the time-dependent case. So this is the part, in the semi-discrete case, so this is the part. We have the damping of the influence of the eigenvector with the corresponding eigenvalues. Now we have something different, maybe also a damping or not, but now it's not done by the E function, by the E part, but it's done by this rational part, this rational function at minus lambda I tau to the n. So we have to analyze what happens with this. So what actually happens, and that is the big deal with using eigenvectors in conjunction with linear ordinary differential equation systems. What we have done, of course, we have diagonalized. Going to the eigenvector basis, we have diagonalized the system of ordinary differential equations. Now we are in the new variables which we have defined by the eigenvector basis, we have a independent sequence of scalar ordinary differential equations, each of which looks like this here, only being determined by the one eigenvalue. And here we see again, depending on the sign of this eigenvalue, we have a strongly decreasing component or a strongly exploding component, and so on. So one could also say it is sufficient to look at this scalar value, this scalar linear equation, which is sometimes called then, I don't know, the model problem, and to see what our time discretization does with this equation. Then we are, so to speak, directly at the level where the lambda I appears. Then we get directly the capital R at minus lambda I tau into the business. And if you see, sometimes you see it presented in this way, that one says, okay, now we look at this model problem, and here we discuss the stability. But the rationale behind is, if we have the diagonalizability, then this is the general situation in the way I explain it. So, so what we would like to have for a method, as I said already, we would like to have that the method is, I do not learn how to handle this kind of thing, but maybe it's the other way again. Oops. We would like to have a method to be non-expansive. Non-expansive is, maybe you know the notion of contractive. Non-expansive is a weaker notion. It says we would like to have a one-step method such that if we apply this method, the same method, so to speak, that is the same underlying problem, but for different initial data, U0 and U0 tilde, then we would like to have that the deviation of the two solutions does not increase. It may stay the same, so that's weaker than saying there's a contraction where we require that it's always diminished by a fixed factor L less than 1, but it's not allowed to increase. That is the minimal requirement we would like to have for a method. So this is far away from having exponential damping. We have seen in our problems exponential damping is quite usual. This is much less required here. And if we now, so if we have this in every step, then of course if we apply this relation recursively, that means in particular that at each time level deviation is at most as big as the deviation at the initial time level. If we write the one-step method in this general form here, you see here again the resolved difference quotient. Bring this to the other side and divide by tau, and the theta comes now from this capital phi comes now, for example, from our different theta functions, so to speak. There's the function r in the back. Then the requirement. So this would be our corresponding theta function, phi function for the theta step methods we have discussed. Then Okay, no then. That would it be. So now we want to discuss under which conditions we have stability. And for that we introduce a notion. We would like to see under which conditions we have non-expansiveness of the method. And what we do here, and this will turn out to be equivalent, we define a very important notion, maybe the most important notion in conjunction with time discretization of partial differential equation. It's the notion of astability. Who has heard this word already? Okay, so in any case, yeah, at least you have heard it. Okay, so what do we mean with astability? So we look at this scalar model problem. We've seen already this is, so to speak, sufficient to do so in the case that we have a diagonalizable matrix. And what we require is require that for this specific model problems we have our method is non-expansive for all. Now this is the important thing. For all lambda, and keep in mind the lambdas are then the eigenvalues in the system situation, for all lambdas with real value positive, and for all step sizes. No step size restriction to have this requirement. Now let's investigate this property, and we have seen already applying the one-step method, our specific one-step method to this model problem is nothing but this method here. We've come through a more complicated way to the function R in terms of the eigenvalue expansion, but if we would now apply it directly, we would again get back this function R. So you see, the answer is quite simple. We have to see where the modulus of this function R is less or equal to 0. That is the requirement we would have to have. And so the requirement is that the modulus of this function is less or equal to 0, at least for all positive tau and for all lambda with with positive real part of the complex function. That means we have to speak here about the full left half of the plane of the complex plane. And to do this more properly, we introduce another notion, namely the notion. So this is the requirement we have. What I said already. This is the requirement we have, and particularly for our eigenvalues, if we now look, so to speak, specifically to a matrix problem, then we can restrict ourselves to the eigenvalues. But of course we have to keep in mind the eigenvalue. We are thinking here about space discretizations. That is, we don't have one fixed AH. We have a whole sequence of AHs, with H going to 0, of course with varying eigenvalues, with increasing in number. So it's not just a fixed finite number of eigenvalues we have to deal with. And we know already what our eigenvalues do, namely they converge to infinity. So to get this a little bit more clearly, we define a new notion, namely the domain of stability. So that just means we have any of these functions R, of the stability functions, on the complex plane, and then we look at the subset of the complex numbers where the R of Z is smaller than 1 in modulus. And this we call the domain of absolute stability for the corresponding one-step method. Now let's compute this. I think we do this in the exercises, so I will not do it explicitly. Now let's compute this domain of stability. Yeah, why is this a reasonable notion? It means for A stability, we would like to have that the full left hand of the complex plane is in the domain of stability. And if this is not so, we don't have A stability. We can only get stability for having a requirement on the tau, such that the minus lambda I times tau is then in the domain of stability, if this is possible. And we see this is always possible. But there's a problem inherent, because our lambda i's, they basically behave, they are not fixed, as I said, they basically behave like one, the largest one basically behaves like 1 over h squared. So in the end, we get a restriction on tau over h squared. This is a stability restriction which has nothing to do with accuracy. So let's have a look at the domains of stability. The simple situation is the explicit Euler method, the theta equals to 1, is a 0 case. So here the function was just 1. We can go back, have a look again at the function. Where is it? It is there. It is theta equals to 1, just means we have the function 1 plus that. So we just asking the question where 1 plus z in modulus is smaller than 1, that is clear. That is just the circle around minus 1 with a radius 1. Okay, this is a part of the left-hand side of the complex plane, but certainly not the full one. So this method is not A-stable. And the other ones, we have to look a little bit more in detail to see what comes out. But let me mention what comes out. For theta equals 1/2, really the full left-hand side of the complex plane, excluding the imaginary axis, belongs to the stability region. It's exactly what we would like to have. So in this sense, this is very good. And if you now look at theta to 1, at the implicit Euler method, it's even better. Then that's the whole complex plane, except of the unit disk around 1. So also the right part belongs to it, excluding this unit disk. So in the sense of A-stability, we could say, wonderful, there's A-stability. If we think a little bit more about it, then one could maybe get a little bit critical about the implicit Euler method, because what is this doing? We will see this hopefully more clearly in the next time. It is damping components which should not be damped. It's damping the right components, those from the left part, that is okay, but it's also damping all the rest. So typically the solutions for the implicit Euler method are too good. The pictures look too nice. And that is very dangerous. All this, if you do computations, then you get colorful pictures. And if they start to look too nice, then you should really get critical about it. Okay, so there are some problems. Let's see what we now have seen. The first thing is, of course, that is a very simple corollary. We can say we have A-stability if the closure of the domain of stability belongs to the left complex part of the... if the closure of the domain of stability contains the left half of the complex plane. So this is the case for theta equals to 1/2 and theta equals to 1. If you look more carefully, we would see this is the case for theta greater or equal to 1/2. So we could also do 0.6 or something like that if there's some reason to do so. At the moment, it doesn't look like that. So Okay, so what we know up till now, let me first maybe finish by looking at this situation. What can we do with the Euler, with the explicit Euler method? We can only get results depending on the eigenvalues, because we would like to we need to have that this situation is fulfilled. And this, of course, gives a requirement for fixed lambda I. This gives a requirement on the tau. Tau must be less than 2 over the maximum of the eigenvalue. The eigenvalue, but as I said already, at least the maximal eigenvalue we are dealing with here depends like 1 over h squared. And here this is made more explicit, again looking at the 5-point stencil on the rectangle. That means in this specific case, we get this step size requirement. Tau over h squared less or equal than 1 over 4. The 1 over 4 doesn't play a role, but there has to be a bound on tau over h squared. And if this is not, that means if you take the tau too large, you would get an unstable development in time. You get an explosion in your solution. You have error components. If they do not exist in the beginning, they will come in just by rounding errors, and they will not stay at their level, but they will get amplified. In every step, more and more amplified. So this forces you, dealing with an explicit method, to deal with very small time steps. So if you halven your age, you have divide your tau by 4. And that, of course, is contradictory a little bit to the advantage which we seemingly have, that we do not have to solve a set of equations here, that we have an explicit method opposite to an implicit method. And the conclusion is that the usual conclusion is the explicit method is of no use in conjunction with partial differential equations. Okay, and about the other two, we have to go on a little bit with our discussion that we do the next time. Okay.